In the previous video, we've introduced the statement of Bezout's theorem. It says that any two complex projective plane curves of degree m and n would intersect at exactly m times n points, if we count multiplicity. In this video, we're gonna give an elementary proof of this using resultant. Well, I should have probably put the word proof in quotes, because instead of doing a formal proof, we are gonna demonstrate how the proof would look like by working with a concrete example. So let's look at this example of 2 degree 2 curves. One is a parabola and the other is a circle centered at the origin of radius 2. According to Bezout, this should have 4 points of intersection, and let's see if we could figure that out algebraically. Now you might wonder, how could these have 4 points of intersection when the picture only shows 2? Well, remember, we also have to count complex points and points at infinity. So the first thing we need to do is to look at the projective completion of our curves. We obtain their formulas by homogenizing these equations. Alright, so now we've got 2 projective curves. How do we find their intersection? And as I've hinted, we want to use resultant, so how do we rephrase this problem in a way that allows us to use resultant? Well, observe that we can think of the xy coordinates of the points in the intersection as follows. So x0, y0 would be the xy coordinate of a point in the intersection if and only if there exists a z satisfying both 1 and 2. In other words, the xy coordinates of the point of intersections are exactly the x0, y0 for which 1 and 2 have a common solution in z. And common solution, that's the word that summoned resultant. If we view these as polynomials in z, then these 2 equations have a common solution if and only if the resultant of f and g with respect to z is 0. If we form the Sylvester matrix and then take the determinant, we'll see that the resultant of these 2 polynomials is going to be given by this expression. Observe that that's going to be a homogeneous polynomial in 2 variables of degree 4, and any such polynomial is going to factor as a product of 4 linear factors. And using exactly the same argument, it's not hard to see that in general, if degree of f is m and degree of g is n, then the resultant of f and g is going to be homogeneous of degree m times n. In particular, it's gonna split into m times n factors over the complex numbers. So here you might be quick to say, okay, it's split into mn factors, so that means the 2 curves have mn intersection points. But we have to be careful. We want to see what is the correspondence between these factors and the intersection points. Okay, so let's see what is the geometric meaning of each of these factors. Observe that each of them determine a line on the plane. So what's the relationship between these lines and points of intersection of these 2 curves? For this, let's recall our original argument. Recall that there exists some z such that x0, y0, z is the point of intersection of these curves if and only if the resultant of f and g with respect to z viewed as a polynomial in xy, right, evaluated at x0, y0, must be equal to 0. And that happens if and only if one of these factors is equal to 0, i.e. if and only if x0, y0 lie on one of these lines. So this factor corresponds to equations of line going through the origin and a point of intersection. For example, these 2 real factors correspond to the lines through the origin and the real intersection points. So even though they do not directly give us the intersection point, we can use them to compute the intersection point. And how do we do that? Well, we take one of these lines and then look at the intersection with one of these curves. Well, but that wouldn't be enough since the line could intersect the curve at points other than the common point of intersection. So we should also look at the intersection of this line with the second curve. And the point here that is common to both of the intersections, namely this yellow point here, is gonna be the common point of intersection of these 2 curves. we repeat the same thing with all the other lines. Alright, so from this you might say, okay, so each of the point of intersection of these two curves determine a line, a factor in here. Thus the number of factors must be equal to the number of common intersection points. So since the resultant of polynomials of degree m and n must have exactly m times n factors, two curves of degree m and n must intersect at exactly m times n points. And QED. Well, that is not quite right. Yes, indeed, each of these intersection points is gonna determine a factor, right? We get that factor by connecting this intersection point to the origin and get the equation of this line through the intersection point and the origin. The problem is that two different intersection points might determine the same line. That is, the correspondence between factors and intersection point might not be 1-to-1. We can see that clearer if we look at that algebraically. Algebraically, we have a map from points in the intersection to the linear factors of the resultant, sending every point a, b, c to the linear factor, which is a scalar multiple of bx minus ay, i.e. the equation of the line through the origin and the point a comma b. Well, the trouble is that different points might determine the same line. So this map is not injective. For example, in this case here, we have a circle and a hyperbola. They intersect at 4 points, just as expected. But observe that two of these points of intersection, these 2 points, actually lie on the same line through the origin, namely this line here. So two distinct points might correspond to the same linear factor. The good news is that would not affect our counting, because in that case, as in this example, that factor is gonna have multiplicity 2. And if 3 points correspond to the same factor, then the factor is gonna have multiplicity 3. So the degree of the resultant is still equal to the number of points of intersection. A more formal argument is as follows. So observe that the number of common intersection between these curves do not change if we perturb each of the curves a little bit. So we can perturb the curves in such a way that no 2 points of intersection are gonna lie on the same line through the origin. That is possible since this lining up is a very special, unstable position. And in that case, each point of intersection will correspond to a unique factor in the resultant. So we have a bijection between number of factors and number of points of intersection. And thus the degree of the resultant must be equal to the number of points of intersection. This roughly proved the Bezout theorem. And sorry, I should have said linear factors instead of factors. Note that we have glossed over the case when the two curves have an intersection point of multiplicity greater than 1, i.e. if they share a common tangent at this intersection point. In this example, this point of intersection is of multiplicity 2. Algebraically, this corresponds to the fact that the corresponding factor to this intersection point in the resultant has multiplicity 2. So observe that that factor should be the equation of the line connecting the origin to the point of intersection, which is just the line y equals to 0. In the resultant, that factor appears with multiplicity 2. To deal with a situation like this, we can just, as before, deform one of the circle a little bit and separate this double point of intersection into 2 points. In the example here, I just moved this green circle along the x-axis a little bit, changing its center from 1, 0 to a, 0. If we compute the new resultant, we'll see that this double factor now become 2 distinct factors corresponding to these 2 lines. Here are their equations. Now observe that as a goes to 1, i.e. this circle, as this circle moves back toward the position of the original circle, this equation becomes y equals to 0. So we should think of this line as the limit of these 2 lines, as this green circle is moving horizontally. It is in that sense that this line is a double line and this factor is a double factor. So those are the key intuitions behind the proof of Bezout's theorem. Using these ideas, it's not hard to see how one would put together a formal proof, and I hope you have fun doing that. Now, intersection multiplicity alone is a deep and complex topic, so we'll discuss that separately in more details in future videos.